This time we will be listening to Łukasz Kucharski. He started programming in his teens. He's gone down enough wrong paths to recognize them and then avoid them. His programming credo is to write such code that when you're fired, then your project is easily taken over. However, the logical thinking is that if you are such an employee, then you are not very likely to get fired. And he likes solid principles, spiced up with Yagni, but his favorite software engineering rule is there are no absolutes, always be reasonable. And at work, on top of working, he likes to have all those discussions which end up in various bets, and those bets are resolved by Godbolt Compiler Explorer. And Łukasz has a case study for us called When Warnings Become Errors, a case study of latent bugs discovered by modernizing toolchain. So the stage is yours. Let's warmly welcome Łukasz Kucharski.
Okay, I think I'm online. Thank you very much for the introduction. As the first word, I would like to reiterate what I've heard on the other talk. All hail Matt Godbolt for his work. I think he's the most prevalent here. Okay, so I know that Rafa didn't mention one thing that this talk is about because it's kind of a taboo and it's we don't like it as we don't like undefined behavior. It's there and we always laugh about it, and it's business. So I want to have a brief moment and talk about how to talk to business to let them do you do fun stuff and modernize your toolchain and compiler to get all the best and newest shiny tools. So yeah, here's a bit about me. If you want to contact me, you can use łukaszkucharski@mentor.com, and if they fire me, you can use yayamiomat@gmail.com. It's my personal email. So here is a brief introduction because it's a case study. So a few words about our code base. It's 5 to 10 million lines long. That's a rough estimate. It's not so easy to count when you have symbolic links in the build tree. It's been developed since 1995, and that makes it lots of legacy code. And also, those were the first commits, so the actual code is a bit older. We are in the process of transitioning from GCC 4.94, and we're using Switch, STD, C++, 1Y, because C++ 14 wasn't fully developed back then. And we've had to do lots and lots of patching and relaxing compiler errors to warnings just to make GCC 9 accepted in the process of transitioning. This is the courtesy of Grzegorz Roszak, who couldn't make it here as an attendee, but we say hi. And to gather the data about the issues, I have hacked run clang tidy to save the compilation information into an SQLite database for the further processing, because there was lots and lots of them. So what I'm going to talk about is with no checks enabled at all. It just had modernize equals defaults because that was our use case, and it still reported almost 2,000 issues that prevented Clang from compiling the code, while GCC we used perfectly accepted it. I also, for the fun of it, ran with all the checks that Clang tidy supports, and there were 3 million issues in our code base, but 2 million of them were magic numbers. So that's to say that not every issue is a fatal one and critical one, but we'll get that there are quite a lot funky ones to play with. So this is the business slide. I'm really sorry that it's wordy, but it's a business slide, so I hope I can sleep with it. So the important here is that the cost of fixing a bug increases exponentially depending on the phase that it was found. And different studies that I found give different estimates. So here on the graph, you can see that it rises about 6 times or 30 times from 1, depending on how you understand requirements in architecture. And IBM report says that a bug found at the client side costs 100 times more to fix than the one identified at some maintenance stage, such as compilation or static check. So if that bug costs developers time in money $100, because I don't know how much your salary is, but let's say that on average 4 hours of fixing is $100, then that found out at client makes it $10,000. So why that happens is because at each stage, especially in enterprise software, different layers of the procedural overhead come in. So when you're a developer and you find a bug, you just fix it, and hopefully no one noticed, no one laughs at you. If it's a code review, then you just go to your friend and say, hey, why are you bit shifting one right and not left? Okay? And if it's QA, then they have to file official QA bug into the ticket system. It needs to get fixed. It needs to get tested again. You understand the thing. If it's an application engineer, it's a buffer between the product and the client. Those reports are even more treated seriously. And when you get to the post-release, so a latent bug at the client code, you can imagine how much paperwork and procedures and layers and people are involved in fixing that. So that's why it happens. And managers often would let you do this work, but they cannot just let someone work for a month or a quarter on something unproductive like modernizing toolbase. It provides no new functionality, so no new value for them. But if you take $1,000 for fixing a bug at the client or manifesting a bug at the client, and you scale that against the code base, like in our example, there were 2,000 hotspots, and I expect that 1/3 to 1/2 are actual places that should be addressed. Not everything is fatal, but they are not perfect, and certainly there are bugs that are just waiting for good conditions to happen to blow up. So if you scale that by $10,000, suddenly your manager can speak to their manager. Like, there is potentially a lot of money, so maybe we should let this guy do the work and let him get his shiny tools so he simply doesn't commit bugs that are easily preventable with those tools. As a bonus, his friends also won't commit those bugs because everyone will be protected through the tooling. And we've had already 2 great talks today, especially the first 2 about the code smells and about the undefined behavior. So I don't have to underline the importance of that to you. So with the remaining time, I hope I will bump up the what the funk factor and get some laughs about what actual bugs were found in our code base. So first, what we got there, logical not is applied only to the left side. So we've actually had those codes, those are anonymized, and they're latent bugs, so it's not that our tool is blowing up all the time. It's just in some place that's not so used. So someone had the idea of putting exclamation mark at the left side. And what this does is it takes the integer value that's result of the function call. It compresses them to 1 or 0 because it's an implicit cast to bool for the exclamation mark. It applies the logical not. And then for the comparison, it gets promoted to an integer. And then it gets compared to the right side. So first 2 examples are tautologies, and compiler tells you that this doesn't make sense, so you probably should check it. I don't think this code works as intended. The vector size, I don't have time to go into the detail how this logic works. It was very funny to debug and understand it, because it works somehow, and compiler cannot tell whether it's right or wrong. And out of 16 cases, we've had 10 bugs. So, and 5 of those only were tautologies, so the obvious places that are some kind of mistake. And six places, sorry, that was a Freudian mistake. I have a Stockholm syndrome with this stuff. 6 places were actually fine, because if on the right side you will place a 0, then the logic works the same. So the places that were fine were comparing to an enum, like OK or some error code, which was 0, and some of them were comparing to a character 0, which happens to be like /0, the null termination character, which happens to be 0. Sorry. Another one. The result of comparison of some big constant and unsigned is always false. So this is similar. This is not super important, but it's obviously wrong. So this comes from all 32-bit codes. There was one talk mentioning it. I think Björn also in his talk thought that when he saw this really big value, he thought it's npos, and it wasn't. But here it is. And found is actually defined as unsigned is actually 32 bits. So when you assign the rfind to it, it will get implicitly converted. And then found cannot be ever as big as max int 64. So I guess that's almost auto says hi. But the code was actually too old. It was just that this warning was disregarded. And I guess that other places in this if prevented him from actually surfacing. Maybe not a big deal, but this is exactly the same error. But here, the message was that the constant 14 compared to a bool is always false. So, okay. Why 14? What's this number? So the DB version 14 is number 14. So how it gets compared to a Boolean? So if you call DB API get version and DB version, how it works is that it stores the value of the DB version into the variable, but it itself returns whether the call succeeded or not. So I hope that nobody uses version more than 14, because then it works the same. Or that the 3 dots were not really that important in there. Okay, this one is interesting. Unused comparison. So some of the unused comparisons were just to shut down the compiler warnings, but this one was really interesting. So what this code does is iterate over 2 containers simultaneously. There is a container with values and container with related values. Cannot say it any better, sorry. But the interesting thing happens on the second line of these 4. So it works pretty normally. It sets up the iterators, and it increases those iterators on each step. But I suppose, I haven't asked the original author, that it should stop whether either of those containers ends. So we have exhausted it. But for some reason, they used comma. And what does comma do is ignore the result. So this is not checked. There should be a logical end in there. And I hope the sizes always match. Okay. This one is pretty funky, I would say. So this is just a parenthesis or operator precedence. That's why on the Jason Turner's talk, I've actually shouted out a wrong answer to his question about some return value. So the operator precedence there was okay, but I still would put some parentheses in there. And here we have some examples where this would happen. So the table size, I presume it should be all the f's, so 2 to the power of 14th minus 1, but actually it's 1 to the power of 13, so it's roughly half the size. I hope the table size is not needed to be actually that big, but I don't know. But our gem is that a ternary operator has lower precedence than a plus. So I presume that the author meant, and this is original formatting with all the spaces, so that's why it confused me in the first place, is to get the number of bits set. So if you check 2 bits, then you probably would expect a value between 0 and 2. But how it works, it checks bit number 0, whether it's true or false, and if it's set, then we return 1, and if not, then we add 0, which is completely redundant here, and we check the next bit. I don't think that's what author meant. There was cases why I'm talking about most vexing parse, because every developer, when there is a problem with the most vexing parse, would probably give their little finger that it's a bug. We've had 12 cases, but none of them were errors. Some of them were generated by Yak and Bison, but we've had errors when the mutex was defined like that. And I won't go into details again because I don't have time and I need to wrap up, but this is a pretty nasty bug to debug, and when it manifests, because it deals with parallel codes, you should correct it. Okay, this one was tricky. If I were to have time, this is a bonus, so I won't talk about it. It's in the slide for you as a homework. This is a summary. Just spend some time to run the static checker, get it from the manager, just a week to do some hacking, pick interesting latent screw-ups. So the manager, say you have the dozen against the million lines code base, hundreds or thousands. Don't lie, base it on the actual data, and show them the cost studies. This really talks to the business people because it's money that can blow up. It should be really easier to get the time to get your new shiny tools. Okay, those are the references. Again, thanks Godbolt, Clang, and GCC, which are not mentioned here. And thanks for your attention.
Thank you very much. Thank you. Thank you, Łukasz. Any questions? If you'd like to come down here and ask a question, as a reward, you can have a bet with Łukasz and then lose it. Thank you for being so brave.
Clang has an option when you got those errors to auto-fix them. Have you tried it?
Yeah, so we actually, the use case was to use the fixer for modernize equals defaults, but we've had a problem with even running it because it reported issues for the compilation. So the run Clang tidy didn't work properly, and because of the symlinks, we couldn't really so easily apply it. So we need to hack the patch processing as well to work with symlinking.
And finally, it worked and fixed all those errors after it compiles, maybe, or how many did it fix?
No. So it found about 5,000 places in our code base for that, but and it fixed it all, but in an incorrect manner. Some of them. So it actually applied the patch a few times if there were 2 valid paths to achieve the file. So that's why we couldn't actually use it.
Okay.
Thank you. Any more questions, please? All right, then. If not, let's thank again Łukasz Kucharski.
Thank you very much.